Hello everyone, it's Mrs. McCready here, and I'm going to take you through today C5 chemical changes for combined science. We're going to cover 4 different topics today. We're going to cover the reactivity series and displacement reactions, extracting metals, making salts, and neutralization and the pH scale. So just to start you off, there's a do now up on the board here. Your teacher can pause the video and then come back when you're ready to go through the answers. So again, there were some fairly straightforward mathematical calculations. The answers are up on the board here. The first one, you just had to do 1,950 divided by 2,500 and then multiply by 100 to get the percentage. Part 2, you had to add up the formula masses from the periodic table. That would have got you 132. A common mistake is forgetting that the 2 outside the NH4 applies to everything inside that bracket. And finally, the question about concentration, you had to convert the volume into decimeters cubed by dividing by 1,000, and then you would have done 1.4 divided by 0.025 to get an answer of 56. So the first thing we're going to talk about today is the reactivity series, and this should be fairly familiar to you. Here is a picture of the reactivity series, and you can see that it lists metals along with carbon and hydrogen from most to least reactive. So it's ordering the metals by reactivity. The way that order has been determined is by how those metals react with other substances. And the more reactive substances will react more vigorously. So in this diagram here, you can see calcium, copper and magnesium. Calcium is reacting most vigorously. You can see the bubbles of gas are most vigorous in calcium's test tube. Magnesium is the next most reactive, and copper isn't reacting at all, so that tells us it's least reactive. If we compare that to the reactivity series on the left, you can see that that's the same order that we see there. Substances that are more reactive can displace less reactive metals from their compounds. So we see displacement reactions happening if we add a more reactive metal to a compound containing a less reactive metal. So here's an example. We've got magnesium being added to copper sulfate. So to start with, copper is part of the compound. Now, because magnesium is more reactive than copper, it can displace it from that compound. And the two products we end up with are magnesium sulfate and copper. You can see that the magnesium has just displaced the copper in this example. If you added a metal that was less reactive than the metal that was in the compound, you wouldn't get a reaction happening. No displacement would occur. So when we have displacement reactions, those displacement reactions are also examples of a type of reaction called redox. And that's a combination word, a portmanteau of reduction and oxidation. Oxidation is when a substance is losing electrons, and reduction is when a substance is gaining electrons. You can remember that using this acronym OIL-RIG. Oxidation is loss, reduction is gain, and the loss and the gain here are both talking about electrons. So let's look at an example of a displacement reaction. We've got zinc sulfate and magnesium reacting together. Again, because the magnesium is more reactive than the zinc, it can displace it from the compound, and we end up with two products, zinc and magnesium sulfate. So the magnesium has displaced the zinc in this example. Our next step is to work out what is happening in terms of the metal ions and atoms. What I've done here is written out an ionic equation, and the ionic equation is showing me the different ions that are taking part in this reaction. If we focus just on the reactants for now, the zinc sulfate and the magnesium on the left-hand side of the arrow, the zinc and the sulfate in zinc sulfate are both ions because zinc sulfate is an ionic substance. So I've got zinc ions with a charge of 2+ and sulfate ions with a charge of 2-. I've also got magnesium as one of my reactants, but that's just a metal, it's not an ionic compound. I've done the same for my products. This time my products are zinc and magnesium sulfate. So zinc is the metal, it's not an ionic substance, so I just leave that as it is. But the magnesium sulfate is an ionic compound, so I split it up into the two ions that it's formed from, Mg2+ and SO4 2-. Now you can see that the SO4 2- will cancel in this reaction because it's the same on both sides. And if I cancel, I end up with my ionic equation in this third bullet point here. Zn2+ ions plus magnesium will form Zn plus magnesium ions. So if I look at what's actually happening here, my zinc ions on the left-hand side of the arrow, the Zn2+, have gained electrons to form zinc atoms in this reaction. We know that gaining electrons is reduction, so the zinc ions have been reduced. My magnesium atoms have lost electrons to form magnesium ions in this reaction. You can see it's Mg on the left-hand side of the arrow and Mg2+ on the right-hand side. So that process involves a loss of electrons, so we know that the magnesium has been oxidized. Okay, the next thing we're going to talk about is extracting metals, and this is also based on the reactivity series that we saw a moment ago. Most metals are found in the Earth's crust as ores. Now, ores are rocks that contain metal combined with other elements, and they contain enough metal that it's worthwhile us extracting them to be able to sell them or to use them in products. Metals that are less reactive than carbon can be extracted from their ores using a process called reduction. And this involves heating that metal ore with carbon, and the carbon will displace the metal from the ore. If you look in the reactivity series, you can see that carbon is more reactive than metals like zinc, iron, tin and lead, and therefore if you add carbon to a metal ore, the carbon will displace the metal from that ore. You'll end up with the metal and you'll get carbon dioxide as your other product. However, metals that are more reactive than carbon won't be able to be extracted using reduction because carbon cannot displace them from their ore. So if the metal is more reactive than carbon, potassium, sodium, calcium, magnesium, aluminium on our table, those metals will need to be extracted using electrolysis. For a couple of metals like gold and platinum, you can see them right at the bottom of my reactivity series, those very unreactive metals are actually found in what we call their native state. So they're found as just the metal, not combined with other elements in ores. Okay, so we're now going to talk about what salts are and 3 methods that we can use to make them. The definition of a salt is that it's a compound formed when the hydrogen ions in an acid are replaced by metal ions. That sounds a little complicated at first glance, but if we look at an example, I've got sulfuric acid on the left-hand side here, H2SO4, and I'm replacing the 2 hydrogen ions in that, in this case, with sodium ions. It could be any metal, but in this case I've replaced with sodium ions. So on the right-hand side you can see the hydrogen has been replaced by sodium, and I've now got sodium sulfate, which is a salt. This would work with any acid and any metal. There are 3 ways that we can make a salt. The first way is adding just a metal to an acid, and those metal ions will replace the hydrogen ions in the acid to make our salt. We'll also form hydrogen as the second product. The second method we can use is metal oxide or metal hydroxide with acid. Again, we'll get a salt. This time we'll get water because our reactants had additional oxygen in. And finally, we can add a metal carbonate to the acid. We get our salt, but this time we get carbon dioxide gas and water. Again, because there is carbon and oxygen in our original reactants. The name of the salt you get will depend on the reactants you use. The first part of the name of the salt will always be the metal, from either the metal oxide or hydroxide, or the metal carbonate. The second part of the name depends on the acid you use. If you use hydrochloric acid, the second part of the name will be chloride. If you use sulfuric acid, the second part of the name will be sulfate. And if you use nitric acid, the second part of the name will be nitrate. So the final topic we're going to talk about today is neutralization and pH. There are 2 definitions for acids and alkalis that you will need to learn. Acids are substances that can release hydrogen ions, or H+ ions, in solution. So you can see, for example, hydrochloric acid, HCl, would split up into H+ ions and Cl- ions in solution. So all acids will release hydrogen ions in solution. Alkalis are substances that release hydroxide ions in solution, or OH- ions. You can see here the example is sodium hydroxide, releasing sodium ions and hydroxide ions. This picture should be very familiar to you. This is the pH scale of universal indicator, and it shows the colour that different substances will turn with universal indicator. A neutralization reaction happens when the hydrogen ions from the acid and the hydroxide ions from the alkali combine to make water. And you can see the ionic equation for that reaction here, H plus OH minus making water, H2O. So if we add an acid to an alkali, we'll get a neutralization reaction happening. pH is a measure of hydrogen ion concentration. The lower the pH, the higher the concentration of hydrogen ions, and therefore the more acidic the substance is. And pH and hydrogen ion concentration are linked in this way. So a hydrogen ion concentration of 1 times 10 to the minus 5 is equivalent to a pH of 5. And you can see that the standard form number up here, the minus 5, is equivalent to the pH. If we look at a second example, the hydrogen ion concentration of 1 times 10 to the minus 3 would be equivalent to a pH of 3. If you go on to do A-level science, you will learn some calculations that let you calculate the pH of any substance rather than using just this simple relationship. But for GCSE, this is absolutely fine. Okay, so we're going to do just 7 quick questions now. Your teacher can pause the video here and give you some time to complete these, and then come back when you're ready to go through the answers. Okay, so the answers. A strong alkali will turn blue or purple in universal indicator. Alkalis release hydroxide ions or OH minus ions in solution. Oxidation is the loss of electrons. Metals that are less reactive than carbon can be extracted using reduction. If they're more reactive than carbon, you'll need to use electrolysis. Magnesium would displace the copper to form magnesium chloride because the magnesium is more reactive than copper. Your two products will be copper sulfate and water. And the two reactants you would need to use to get those products would be magnesium carbonate and hydrochloric acid. Okay, so we're now going to tackle some exam style questions. The first one is up here on the board, so your teacher can pause the video here, give you some time to answer this, and then come back when you're ready to go through the answer. Okay, so you should have had a 4 in front of the Na to balance the 4 sodium atoms on the right-hand side of the equation. This is oxidation because the sodium atoms are losing electrons to form sodium ions. The colour would be purple for a strong pH of 14, and the name of the salt produced would be aluminium chloride. This is the second of the 3 exam style questions, so again your teacher can pause the video here and come back when you're ready to go through the answer. The products of this reaction will be potassium chloride and beryllium, and it is a displacement reaction. So potassium is more reactive than beryllium, so it can displace it. Beryllium isn't on the reactivity series that you would have seen at GCSE in any textbook, but you can see that a reaction happens. They tell you that in the question, so that tells you that potassium is more reactive than beryllium. Part C says explain why this would not have taken place if they'd used copper with beryllium chloride. Obviously copper is less reactive than beryllium, so it won't be able to displace it from the compound. Our final of the exam style questions is up on the board here. Again, your teacher can pause the video here, give you some time to answer, and then we'll come back and go through it in a moment. So carbon can be used because it is more reactive than iron, so it can displace it from iron oxide. The balanced equation was quite tricky here. You've been given the formula for the iron oxide, Fe2O3, and you know that you're adding carbon or C to it. You know that your product will be iron metal, and you'll also be getting carbon dioxide being produced in that displacement, and then it's a matter of balancing. The aluminium is more reactive than carbon, so it cannot be displaced in the same way that iron could be, and you'd have to use electrolysis instead to extract the aluminium from aluminium oxide. Okay, that is the end of this session today on C5 Chemical Changes for Combined Science. Really well done. We've covered 4 topics today: the reactivity series, extracting metals, making salts, and neutralization and pH. If you've still got some time left during this lesson, you could go over some of those concepts again, or if you want to see any parts of the video again, you can ask your teacher to go through that with you.